In last lecture, we have discussed valence bond representation of tetrahedral complexes and square planar complexes. Today, we are going to discuss valence bond representation of octahedral complexes. Okay, so this is very important point. Before that, we have to discuss the valence bond picture of trigonal bipyramidal complexes. Let us consider example of pentacarbonyl iron. Okay, pentacarbonyl iron. So FeCO5, atomic number of Fe is 26, electronic configuration is 4s2 3d6. No charge on this square bracket because carbonyls are neutral molecules, neutral ligand. So Fe0, on Fe there is zero charge and electronic configuration remains as it is 4s2 3d6. So start box diagram. Electronic configuration of iron in ground state. So 3d orbital contains 6 electron, s orbital contains 2 electron. For this trigonal bipyramidal shape, we require dsp3 hybridization. But in this ground state configuration, we observe that d orbital is not vacant. So see this step. In this step, there is pairing of all electrons and iron make one d orbital available for hybridization. This is very important step. In ground state, there are 6 electrons. Each orbital is filled or upfilled, and hence now to vacant d orbital, here there is pairing of all electrons. Got it? And in this way, these are totally 8 electrons, and here now there are again 8 electrons. And now these d orbital, s orbital, 3p orbitals combine together, and there is formation of 5 hybrid orbitals. dsp3 hybridization forms 5d hybrid orbitals. These are, when complex is formed, carbonyl donates electron pair to iron. So in this way, 1, 2, 3, 4, these are the electron pairs from iron, and these are 5 electron pairs donated by carbonyl ligand in dsp3 orbitals. So in this complex, no unpaired electron, it contains 0 unpaired electron. Hence, observed and calculated magnetic moment for this complex is 0, and therefore this complex is dimagnetic. As complex contains 0 unpaired electron, complex is dimagnetic. These are the other examples for this hybridization: MnCO5, ruthenium, RuCO5, and osmium pentacarbonyl. Now see very important valence bond picture, and that is of octahedral complex. Valence bond picture of octahedral complex. There are two types of hybridization. First one is D2sp3 and second one is sp3d2. Let us see first one, D2sp3. The atomic orbitals involved in this hybridization are dx square minus y square and dz square of n-1 cell. S orbital of last cell n as well as 3p orbitals are also of last cell n. What is mean by this? If the value of n is 4 at that time, this is 4s, this is 4p3, but here there is n-1, that means 3d. 4 minus 1, 3d. So that means 3d, 4s and 4p orbitals are used for this hybridization. D2sp3. Let us see examples in which we are going to discuss metal ion undergoes D2sp3 hybridization. First example, CONH36 3+. So 6 ammonia molecules are attached to cobalt. These are neutral molecules and this 3+ charge is from cobalt. Atomic number of cobalt is 27. Electronic configuration, we know it. It is 4s2 3d7 in ground state. And when there is 3+ charge, so CO3+ ion, for this purpose, cobalt must lose 3 electrons, hence 2 electrons from this 4s orbital and 1 electron from this 3d orbital. So electronic configuration becomes 4s0 3d6. Got it? So this is the box diagram for CO3+ ion. 3D contains 6 electrons. No electron is present in 4s orbital. Alright? So D2sp3 hybridization we require, but here these 2d orbitals are half filled, and to make these 2d orbitals available these 2d orbitals for hybridization, what happened? There is pairing of this electron. Here there are 6 electrons. All these are now paired in next step. So these are also 6 electrons. Got it? And 2d orbitals are made available by cobalt ion for hybridization D2sp3. So 2d 1s 3p orbital combines together and there is formation of 6 hybrid orbital. Remember well, hybridization is D2sp3. And in this 6 hybrid orbital, ammonia molecule which is acts as ligand, 6 ammonia molecule donates 12 electrons, and in this way there is formation of coordinate covalent bond between cobalt ion and ammonia. We observe here there is no unpaired electron. Okay. So see, cobalt ion in ground state contains 4 unpaired electrons, but in excited state there is pairing of electrons in d orbitals and 2 vacant d orbitals are created. This is discussed by us. This complex contains 0 unpaired electron, no unpaired electron is present, and therefore it is diamagnetic and calculated as well as observed magnetic moment is 0. Second example, FeCN6 3-. There are 6 cyanide ions which acts as a ligand attached to iron. Here there is -3 charge. How it is created? See, there are 6 cyanide ions, so -6. So for this -3 on Fe there must be +3. Atomic number of Fe is 26. This is the electronic configuration in ground state 4s2 3d6. On Fe there is 3+ charge, we have discussed this, and therefore there is loss of 3 electron from this configuration. Hence it becomes 4s0 3d5. 2 electrons from 4s orbital, 1 electron from this 3d orbital is lost. So 4s0 3d5. See this electronic configuration of Fe3+, 3d orbital contains 5 unpaired electrons. No electron is present in 4s orbital as well as in 4p orbital. Now for hybridization we require 2 vacant d orbital. But here in ground state no vacant d orbital is present. So what happened? All these 2 electrons get paired. Got it? So in this way 2 electrons are paired, 1 is unpaired. So in this way 5 electrons are present in d orbital, same to that of this step. And 2 d orbitals are made available for hybridization. So D2sp3 hybridization is shown by iron. So 6 hybrid orbitals accepts 6 electron pairs from cyanide ligands. These are again original 5 electrons from this step. So 5 electron from iron and 12 electrons from cyanide ligand in D2sp3 hybridized orbit. See now, here there is one unpaired electron is present. See this, in ground state Fe3 plus have 5 unpaired electrons which are paired up in excited state and 2d orbitals are made vacant. Hence, this complex contains one unpaired electron. Got it? Observed magnetic moment is 2.3, calculated is 1.73. These are close to each other. And now the complex is paramagnetic because one unpaired electron is present. Example number 3, CrCN6 3 minus, charge is 3 minus. Again there are 6 cyanide ligand, so minus 6. On chromium there must be plus 3 charge, then and then here there is minus 3. Got it? So minus 6 plus 3, it becomes minus 3. Chromium atomic number is 24. Electronic configuration is 4s1 3d5. There must be loss of 3 electron. Hence this 1 and 2 electrons from 3d orbitals are lost to form Cr3 plus ion. And hence this is 4s0 3d3 configuration. See this Cr3 plus contains 3 electrons in 3d orbital. So 2 d orbitals are vacant for hybridization, for which is d2 sp3. So d2 s and 3 p orbitals combine together to form 6 hybrid orbitals. Hybridization is d2 sp3. In this 6 hybrid orbital, again cyanide donates 12 electrons. That means 6 electrons pairs are donated. And this 3 unpaired electron remains as it is in 3d orbital. So this complex contains 3 unpaired electrons. Observed magnetic moment is 3.87. Calculated magnetic moment is 3.88 Bohr magneton. As 3 unpaired electrons are present, this complex is paramagnetic. Next complex, this one, CONH3 6 2 plus. On this complex there is 2 plus charge because ammonia are neutral molecule. That means cobalt have 2 plus charge. CO2 plus ion is formed. This is the ground state electronic configuration 4s2 3d7. To form CO2 plus ion, there must be loss of 2 electron and hence 4s0 3d7 is the electronic configuration of CO2 plus ion. See this one. So no electron is present in 4s orbital, no electron is present in 4p orbital, but 7 electrons are present in 3d orbital. But we know that for d2sp3 hybridization, we require 2d orbital vacant. Vacant 2d orbitals we require for d2sp3 hybridization. Hence, there is pairing of third electron and one electron is promoted, excited into d orbital, 4d orbital. That means these are 6 electron, this is 7th electron. See here, 3d contains 7 electron in CO3 plus ion. Here also there are 7 electron, 6 one and this is 7th one. In this way, 2d orbitals are available for hybridization d2sp3. So 2d, 1s, 3p combines together to form 6 hybrid orbital 1, 2, 3, 4, 5, 6. Now this 6 hybrid orbital accepts 6 electron pair from ammonia neutral molecule. Okay, and here there are 6 electrons are present in 3d orbital as well as one unpaired electron is present in 4d orbital. So in this way, there is one unpaired electron is present and the complex is paramagnetic. Magnetic moment observed and calculated is 1.78 Bohr magneton. Remember well, for d2sp3 hybridization, 2d orbitals are required. These are available by cobalt by promoting, exciting 7th electron to higher energy 4d orbital. So this is about this cobalt complex. See now other examples. In this example, the hybridization is D2sp3. Remember well. CO CN6 3 minus, Mn CN6 3 minus, Cr CO6 Cr NH36 3 plus. Then see next hybridization sp3d2 hybridization. In this hybridization, 1s, 3p and 2d orbitals are involved. That is dx square minus y square and dz square. But these are from next cell, that is 4d. See here, example Fe F6 3 minus. We know that electronic configuration of Fe, which has atomic number 26, is 4s2 3d6. Here on Fe there is 3 plus charge because fluoride 6 ion, therefore minus 6, and for this 3 minus on Fe there must be 3 plus charge. So Fe3 plus. To form this Fe3 plus ion, there must be loss of 3 electrons, 2 from 4s orbital and 1 from 3d orbital. So electronic configuration for Fe3 plus ion is 4s0 3d 5. So see here, there is no electron in 4s orbital as well as in 4p, and this is 4d. Okay, this is 4d. Now 3d contains 5 electron as we have discussed in case of Fe3 plus ion configuration. 3d contains 5 electron. And now see, in this case 1s, then 3p orbital of 4p as well as 2d orbital of next cell combined together undergo sp3d2 hybridization, form 6 hybrid orbital in which fluoride 6 fluoride ion donates 6 electron pair. There is formation of coordinate covalent bond between ligand and ion. So these complex contain 5 unpaired electron. It is highly paramagnetic. So observed and calculated magnetic moment is 5.92, and the complex is called as highly paramagnetic compound. Then see second example, example number 2, NiNH3 2 plus, ammonia 6 ammonia molecule, neutral molecule, no charge. That means this 2 plus charge is from nickel. So nickel atomic number is 28, 4s2 3d8 configuration, ground state configuration. On nickel there is 2 plus charge. We have discussed this. So Ni2 plus, for this purpose there is a loss of 2 electron from 4s orbital. 3d consists 8 electron. So nickel in ground state 3d contains 8 electron, 4s2 contains 2 electron. In excited state, for formation of Ni2 plus there is loss of 2 electron from 4s orbital. 3d contains 8 electron. No electron in 4p orbital as well as in 4d. This is 4d. Now see, there is a combination of these 1s orbital, 3p orbital and 2d orbital. So there is formation of sp3d2 hybrid orbital. 6 hybrid orbitals are formed. sp3d2 hybrid orbitals are formed, in which 6 ammonia molecule donates 6 electron pair, and there is formation of this complex. Say 3d contains 8 electron. This electron remains as it is. Here there is presence of 2 unpaired electron. Hence this complex is paramagnetic. It contains 2 unpaired electron. Observed and calculated magnetic moment is 2.834 magneton. Followed. Next example, zinc NH36 2 plus. Okay, zinc atomic number is 30, 4s2 3d10. This is the ground state configuration. Again here, C6 ammonia molecules are neutral. This 2 plus charge is from zinc. There is formation of Zn2 plus ion. and for this purpose these two electrons from 4s orbitals are lost. So electronic configuration becomes 4s0 3d10, which is shown in this step. So 3d contains 10 electron, 4s contains 0 electron. This is ground state. 3d contains 10 electron, 4s contains 2 electron. These 2 electrons are lost to form Zn2 plus ion. No electron is present in 4s orbital. Okay, 3d contains 10 electron. Now this s, this 3p and this 2d orbital from 4d combine together and undergoes sp3d2 hybridization. So there is formation of 6 equivalent hybrid orbital in which 6 ammonia molecule donate 6 electron pairs to form coordinate covalent bond. 3d contains 10 electron, this contains 12 electron, no unpaired electron is present. That means this complex contains 0 unpaired electrons. Observed and calculated magnetic moment is 0. Therefore, this complex is dimagnetic. Other example for this hybridization sp3d2, these are FeNH3CH2 plus, CrH2CH2 plus, cobalt hexafluoride 3 minus. Okay, so this is about valence bond picture representation of octahedral complex. We have discussed two types, D2sp3 and sp3d2. Now see next point, what is inner and outer orbital complexes? Inner and outer orbital complexes. Let us discuss with the help of example. We have already discussed this. FeCN6 3 minus. Atomic number of Fe is 26. 4s2 3d6 ground state configuration. Again on Fe there is 3 plus charge because 6 cyanide ion minus 6. Here we require minus 3, therefore on Fe there must be plus 3. Plus 3 minus 6, it becomes minus. So Fe3 plus electronic configuration is 4s0 3d5. See, this is the box diagram. Fe3 plus contains 5 electron. No unpaired electron is present in 4s orbital. Metal ion must undergo D2sp3 hybridization and iron make available this 2d orbital by pairing the electron. Hence here there is pairing of these 2 electron. This electron remains unpaired. 2d orbital 1s and 3p orbitals combined together, there is formation of 6 hybrid orbital D2sp3. 2d 1s 3p orbital combines together D2sp3 hybridization, in which 6 cyanide ion donates 6 electron pair, and this is the configuration for this complex. Now see here, one unpaired electron is present and therefore this complex is paramagnetic. This is the magnetic moment, observed magnetic moment 2.3 Bohr magneton, calculated is 1.73 Bohr magneton. Then see another example, FeFH6 3 minus. See, in previous complex FeCN6 3 minus, we have used D2sp3 hybridization. Inner d orbital is used, therefore it is called as inner orbital complexes. We have used 3d orbital for hybridization. Here see, this is different complex. Fe26 again 4s2 3d6. On Fe there is plus 3 charge, minus require here minus 3, therefore on Fe there must be plus 3. To form Fe3 plus ion, 3 electrons are lost, 4s0 3d5. So these two, 1 from 3d and configuration become 4s0 3d5. Same is shown here, 3d contains 5 electron, no electron in 4s orbital, 4p orbital as well as in 4d orbital. In this complex, what happens? Metal ion use this 2d orbital, 4d orbital for hybridization, sp3d2. Okay, 4d orbital is used. In case of previous complex, 3d orbital is used. This is the difference. Therefore, Fe ion now contains 5 unpaired electron, and these 12 electron from ligand which are accommodated in 6 hybrid orbital. Okay, then say this contains 5 unpaired electron, magnetic moment 5.90 T Bohr magneton, and the complex is highly paramagnetic. Okay, so in efficiency 3 minus we have discussed n minus 1 d2 ns np3 orbitals are used for hybridization. N is equal to 4, therefore this is n minus 1, 4 minus 1, that means 3d2, 4s, n is equal to 4, 4s and 4p3. Okay, 3d2, 4s, 4p3 orbitals are used for d2sp3 hybridization. Okay, the metal which use this type of hybridization, okay, these complexes are called as inner orbital complexes. While we have discussed in case of FeF6 3 minus in this complex, what happened? The iron, okay, use Ns, Np, Nd, N is equal to 4, that means 4s, 4p, 4p orbitals for hybridization sp3d2. Outer d orbital is used, and therefore these are called as outer orbital complexes. This is the difference, okay, between inner orbital complexes and outer orbital complexes. Again I repeat, in case of inner orbital complexes, n-1 d2 ns np3 orbitals are used, that is d2sp3 hybridization. In case of F6 3 minus ns np nd orbital, that means sp3d2 orbitals are used for hybridization, therefore they are called as outer orbital complexes. These are the examples of inner orbital complexes: Mn6 4 minus, CrNH363 plus, etc. Similarly, these are the examples of outer orbital complexes. So this is the difference between inner and outer orbital complexes. So friends, we stop here. In next lecture we discuss next point. We discuss about electroneutrality principle as well as multiple bonding, or which is also called as back bonding. Thank you.